Swayam Prabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering, and today we shall discuss about the ideal cycle of steam power plant. But before going to discuss about this particular cycle, I would like to discuss about a few thermodynamic aspects and also the performance measuring parameters essentially for the steam power plant. If we try to recall, in the last lecture we have discussed about the in fact last two lectures we have discussed about the basic components, rather the major components of steam power plant. We have seen the block diagram, and by applying the combined first and second law to the processes of steam power plant, we could establish the amount of heat, rather the amount of energy must be added to the system in the form of heat, and also the amount of energy which will be obtained from the power plant in the form of net work. And we have seen that the second law together with the first law applied to steady state steady flow processes, rather reversible steady state steady flow processes, whether the process is adiabatic or process is isothermal, the expression of work done for both these processes, that is reversible adiabatic and reversible isothermal, but the process must be a steady state steady flow process, the expression of work done is minus VdP. So, in continuation of that, today let us again draw the block diagram of the thermal steam power plant. So, this is what we have seen in the last class. Now, you can see that here, let me again write this. B stands for boiler, T for turbine, P for pump, and C for condenser. So, what we can see from this particular block diagram, that is the steam power plant, though we can see only 4 major components, there will be several other minor components but two important points I would like to mention today, that if you would like to know the performance of the plant itself, we need to analyze all the processes, I mean the process which is there, the pumping process, boiling of liquid, expansion of steam inside the turbine, and finally condensation of steam in the condenser. So, to obtain the performance of the plant, we need to analyze all the processes, and if we need to do that, we need to map all these processes in thermodynamic coordinate diagram. So, that is we have seen. Now, also we can see that this unit of this power plant operates in a cyclic manner, that you can easily see from this symbol. This is a restriction posed by the second law of thermodynamics, that if you would like to run this unit in a cyclic manner, essentially to have continuous work output, we must supply heat continuously to the system, which is most important is that there must be a provision of rejection of heat from the system that we can see. Okay. So, this is very important. Now, what I said, that we would like to analyze the performance of this plant. We can analyze the performance of this plant or system by mapping all the processes in thermodynamic coordinate diagram. Importantly, whenever we will try to map all these processes in coordinate diagram, we need to compare this with a cycle, because it is a cyclic, the system is or unit of this plant is running in a cyclic manner. So, to obtain the performance, we need to compare the processes with the processes which constitute together to form this cycle by comparing with a thermodynamic cycle, right. So, you know that, let me write here, performance of the unit of power plant. So, if you obtain, if you would like to obtain it, we have identified all the processes, all these processes constitute together to form this cycle, and as if the system is running in a cyclic manner, and finally, we need to compare this particular unit, the cycle of this unit with a thermodynamic cycle. So, basically cycle is compared with a thermodynamic cycle. So, which is this cycle? So, you know that if I try to write over here, processes, so all the processes constitute together to form this cycle. Okay. So, basically we need to compare this with a thermodynamic cycle. Now, what is the need of studying the thermodynamic cycle, right? You have studied this in the basic thermodynamic course. Thermodynamic cycle, the purpose of studying the thermodynamic cycle, or the purpose of thermodynamic cycle is to either produce power or to produce refrigeration. So, here this is the symbol represents that the working substance, all the processes are getting executed in a cyclic manner. The working substance undergoes through several processes following this cycle, and that cycle needs to be compared with a thermodynamic cycle essentially to obtain the performance of this plant. Because you know that we in power plant, our first and foremost objective should be to measure the performance. Why? Because at the cost of this input energy we are getting some output, some energy output. So, all this heat which is supplied to the boiler will not be converted equally to the work which is getting produced here, and perhaps it is because of this reason that this heat is referred to as the low grade energy and work is referred to as the high grade energy. So, try to understand, maybe a certain fraction of energy, that certain fraction of the input energy will be there in the form of work from the turbine. So, hence the efficiency is very very important. Why? So, by knowing the efficiency, what we can do, we can take several measures to improve the operational aspect of this plant to enhance the efficiency. Okay. So, a thermodynamic cycle, let me write here today. So, this thermodynamic cycle purpose is to produce, either to produce power or to produce refrigeration or pumping of heat. Right. If the objective is to produce power, then the cycles are known as power cycles. If the objective is to produce refrigeration or pumping of heat, then it is known as refrigeration cycle or the heat pump cycle. So, basically that from there we can understand. So, thermodynamic cycle can be broadly classified into two categories. One is the power cycles, another is or cycle. Okay. So, that I am just trying to recapitulate whatever you have learned from basic thermodynamic course, essentially to have consistency in understanding whatever we are going to discuss today. Okay. So, that power cycle, or which is commonly known as heat engine, since in this particular module of this course we are going to discuss about the steam power cycle. So, you can understand we shall focus our attention on this power cycle. So, objective, if we go to the previous slide, as we have written over here, that the cycle should be compared with a thermodynamic cycle, and that thermodynamic cycle should be the power cycle that we can see, that we can understand from this. Okay. So, the power cycle, that again what you can see. So, basically the power cycle should be operated using a particular type of working substance. So, you can see that the working substance for this particular cycle is steam water and steam. So, the power cycle in general, whether it is power cycle or refrigeration or heat pump cycle, the working substance is an important. So, the power cycles are operated as the gas power cycle or vapor power cycle. So, let me write over here that power cycles are operated as the vapor power cycle or the gas power cycle. See, this classification or sub classification is based on the type of the working substance that is used. So, whether the power cycle will be vapor power cycle or the power cycle will be gas power cycle, the sub classification depends on the type of the working fluid that is used working substance. For the vapor power cycle, you know, the working substance is water and steam, right. Since the working substance is water and steam, the name steam is there. Sometimes this vapor power cycle or cycles are known as steam power cycles, right. So, I may use this terminology, that is steam power cycle or vapor power cycle. So, I would like to mention here that whether it is steam power cycle or vapor power cycle, so these are the same. So, basically the working substance, hence the working substance is steam. So, we also can call it steam power cycle. On the other hand, though it is not included in this particular syllabus, but you know that maybe in one of the module I will briefly touch upon this particular aspect, but therein I will be discussing in detail, but for the sake of completeness, let me write here, in this particular cycle working substance is gas. If it is air also, so this is basically air standard or air power cycle that you have studied. So, fine. So, what you can see that our objective today would be to learn about steam power cycle, right. So, if we go to the next slide, steam power cycle. Or vapor power cycle. This cycle operates, okay. So, steam power cycle or vapor power cycle, basically these two are the same, but the steam power cycle operates on the vapor power cycle considering steam as the working substance. So, the steam power cycle operates on the vapor power cycle considering steam as the working substance. Now, here I have written about the thermodynamic cycle, right. So, produce power, since power cycle is the thermodynamic cycle, we have to understand what do we mean by thermodynamic cycle. So, you know that vapor power cycle is also a thermodynamic cycle. Since the working substance is steam, we are calling it steam power cycle, which operates on the vapor power cycle considering steam as the working substance. So, what do we mean by thermodynamic cycle? Thermodynamic cycles are basically closed cycle. So, let me write over here. Thermodynamic cycles are closed cycle. What do you mean by that? That means the working substance undergoes a series of processes and is brought back to the initial state. Let me go to the previous slide. So, here I would like to complete that the steam power cycle operates on the vapor power cycle considering steam as the working substance. Here I am writing the steam is converted from water only. So, the steam is converted from water only and that is why we also can call it water steam mixture. So, this is now thermodynamic cycles are closed cycle. If we go to the, this is also steam power cycle which operates on the vapor power cycle considering working substance is steam. So, here working substance is steam water or water or steam. So, you know that in one part of the cycle working substance is remaining as water, in other part of the cycle the same working substance is getting converted into steam. But try to I would like to mention here that water is getting converted into steam, but the composition is not getting changed. So, basically when I am talking about these thermodynamic cycles which are closed cycle, where the working substance undergoes a series of processes and is brought back to its initial state. Is this good enough to call a cycle is a thermodynamic cycle? I may add here that the working substance undergoes through a series of processes and is brought back to its initial state. So, here try to understand, if we start from section 1, what is the state of the working substance? Saturated liquid, right. This saturated liquid is pumped to the boiler, and from the boiler to the turbine till condenser the working substance state is vapor, steam. But so basically the working substance undergoes through several processes like pumping process, boiling, and then expansion, finally condensation. So, you know that all these processes are executed using either water or steam, but eventually at the end of the cycle again we are getting water. So, it is a thermodynamic cycle. So, it is closed cycle, and most important point that I would like to mention here that the composition of the working substance does not change at the end of the cycle. So, maybe we are starting from point 1 considering or taking the working substance as the saturated liquid, at the end of the cycle again we are going to get water only. So, and during the cycle the composition of the working substance is not getting changed. So, this is very important. Fine. Now, so the vapor power cycle or steam power cycle, vapor power cycle being a thermodynamic cycle, it is also a closed cycle. Okay. So, this vapor power cycle is also a closed cycle. Okay. So, now I would like to discuss about one important point that is very important, that coming to the objective. So, if you try to recall that we need to discuss about ideal cycle. So, why do we need to study this particular cycle? Because we need to measure the performance of the steam plant which is operating on this vapor power cycle, right. So, if we go back to the previous slide, here we can list down several processes. What are the processes? 1 to 2, 2 to 3, 3 to 4, 4 to 1. Just I will be writing in the next slide. 1 to 2 is a pumping process, 2 to 3 is the boiling, 3 to 4 is the expansion of steam inside the turbine, and 4 to 1 is condensation. So, you know that here if we write that 1 to 2, that is pumping process, 2 to 3 is the boiling of liquid, basically pumping of liquid. Okay. 3 to 4, that is reversible adiabatic expansion. So, I am writing for the timing expansion of steam. Pumping, that is reversible adiabatic steady state steady flow process. Boiling, this is a constant pressure heat addition. Expansion of steam, reversible adiabatic expansion, and finally 4 to 1, that is condensation of steam. So, this is again constant pressure heat rejection. So, I am not going to describe their thermodynamic name, but for the time being you can understand pumping, boiling, expansion and finally condensation. So, these are the mechanical names. Pumping process, that is reversible adiabatic process, steady state steady flow. All the processes are considered to be steady state steady flow only for the analysis purpose. Boiling of liquid, that is constant pressure heat addition inside the boiler. Expansion of steam, that is again reversible adiabatic expansion, and finally condensation of steam, that is constant pressure heat rejection. So, when we are trying to have the performance of the plant unit, we consider all the processes are ideal, right. So, considering all the processes are to be ideal processes, we measure the ideal cycle efficiency. So, I am writing, we consider all these processes are ideal and measure the ideal cycle efficiency, right. So, we consider, again I am telling these are the mechanical names, considering all these processes are ideal and measuring the performance of the individual processes, we consider, we calculate the performance of the cycle which is constituted by all these processes. Okay. So, the efficiency that we will get following this exercise is the ideal cycle efficiency. So, I am underlining this. So, this is ideal cycle efficiency, right. But you have studied in thermodynamics, see why I am recalling that you have studied this thermodynamics like this. This subject is applied thermal engineering, basic and applied. So, basically the basic understanding of thermodynamics will be very much helpful to understand whenever we are trying to apply those concept in applied areas, applied field. So, you know that you have studied in thermodynamics that whenever, again if I go back to the schematic depiction, that will help us to understand. See, to some extent irreversibility will be there, whether the liquid is pumped from 1 to 2 and when the liquid is heated inside the boiler and it is converted into steam at state point 3, and when the steam is allowed to expand inside the turbine following reversible adiabatic process, or even if we consider here that the steam which is taken to condenser for the release of heat to the ambience, all these processes are not ideal in reality. So, in real practice, if we consider some degree of irreversibility will be there, or some degree of irreversibility is associated with all these processes. So, knowing that some degree of irreversibility will be there, we just cannot trivially ignore the actual process should be different than the ideal process. So, if we go to the slide, though we can consider all the processes are ideal, but accounting for this particular issue that some degree of irreversibility will be there in all processes, all the processes will not be the ideal processes. Rather, I can tell you no process in reality is an ideal process. So, what we need to do, instead of considering the concept of ideal process, we must consider that all these processes are not ideal because irreversibility is there. So, what we need to do? We need to consider actual process. So, basically the efficiency that we are considering, efficiency that we are calculating considering all the processes are to be ideal, it is the ideal cycle efficiency, but at the same time we need to consider that all the processes are not ideal, rather they are actual. So, we need to introduce the concept of process efficiency. So, basically I am writing, so considering the presence of some degree of irreversibility actual process efficiency needs to be calculated. Right. So, if you would like to knowing fully that some degree of irreversibility is present in all these processes, what we can do? We can introduce the process efficiency, individual process efficiency, that is actual process efficiency. If we integrate them, all these mechanical processes that we have listed down, all these mechanical processes. So, irreversibility is there in the pumping process, some degree of irreversibility is there in the boiling of liquid process, some degree of irreversibility is there while steam is getting expanded in the turbine, some degree of irreversibility is there when steam is getting condensed inside the condenser. So, considering all this irreversibility, what we need to do? We need to calculate individual process efficiency, and then if we integrate them, we can get actual cycle efficiency. So, by calculating the actual process efficiency, there are 4 different processes we have so far understood. So, calculating the actual process efficiency for all these 4 processes, we can calculate the actual cycle efficiency because all these 4 processes constitute the cycle. So, now, so basically we have understood from this particular slide that we can consider all the processes are ideal, because you know that if we need to map the processes in thermodynamic coordinate diagram, we have to consider that all these processes are ideal, and at the same time we must admit that some degree of irreversibility will be there. So, accounting for this particular thermodynamical issue, we need to consider, we need to calculate actual cycle efficiency. So, now the ratio of the ideal cycle efficiency to the actual cycle efficiency, or is known as the relative efficiency of the plant or efficiency ratio. efficiency ratio. So, let me again underline these two lines. So, the relative efficiency or efficiency ratio. So, can you tell me, knowing fully that in real practice all the processes are not ideal, so why do we need to study this ideal cycles efficiency? Why do we need to calculate this ideal cycle efficiency and consequently the efficiency ratio? So, this is very important to understand, because this is the measure of, this is used as the measure of perfections of all real cycles. Try to understand. Let me give you an example. See, you have studied about fluid mechanics, you have studied about thermodynamics, you have also studied about heat transfer, at least these three important subjects in thermal fluid sciences. So, you know that you have studied about ideal fluid. It is very difficult to obtain a fluid which would be ideal, but still we need to study the behavior of the ideal fluid. Why? Objective is why the same, because we know a priori that it is very difficult to maintain a process to be ideal process in real practice, even though we need to study that, and studying that we need to calculate the ideal cycle efficiency. And not only that, by knowing this, we are also introducing this word, that is relative efficiency or efficiency ratio. Objective is this particular relative efficiency of the plant or efficiency ratio of the plant is used as the measure of the perfections of the actual cycle which are there in the real applications. So, let me write here. So, this particular term, this efficiency ratio, let me write, this is, I am writing this. So, this is used, this is used as the measure of perfections achieved in actual cycles. So, basically this is the ideal one, but in reality we will be getting actual one. Our objective should be to go for improvement of the actual cycle to achieve the ideal one. So, basically if the efficiency ratio is equal to 1, that is the, so our objective should be not to reach at efficiency ratio equal to 1. So, that is not possible at all, but closer to 1. So, that is why we study this. So, this is why I have written this is used as the measure of perfections achieved in actual cycles. Okay. You know that this is very important. Now, so we have understood that though it is very difficult to achieve a cycle to be ideal cycle in practice, but still we need to study it. Why? Only to measure the perfections that will be achieved in real cycle. You know that there are among the ideal cycles, the Carnot cycle is considered first, that you have studied in thermodynamics. I am not going to discuss about all those part, but among the ideal cycles, Carnot cycle is considered first, and subsequently all actual cycles are considered, right. So, accordingly the ideal vapor cycle would be the Carnot vapor cycle. Okay. So, let me repeat, among the ideal cycles, the Carnot cycle is considered first, and subsequently all actual cycles are considered. So, accordingly the ideal vapor cycle, that is what we are going to discuss today, should be the ideal vapor cycle, should be the Carnot vapor cycle. Okay. So, you know that I will be writing over here this ideal vapor cycle, and it should be the Carnot vapor cycle. So, you know that this Carnot vapor cycle, you know, you have studied in thermodynamics. This cycle comprising of two isothermal and two adiabatic processes, right. But you know that is very important that though Carnot cycle you have studied that the Carnot cycle comprising of two reversible isothermal and two reversible adiabatic processes. We shall be discussing those part. But before I go to discuss, I would like to discuss about a few important thermodynamic aspects, like what do mean by work ratio, what do mean by back work ratio, etc. Right. So, you know that so this Carnot vapor cycle which comprising of two reversible adiabatic and two isothermal processes. We shall be discussing this particular cycle, but as I have mentioned just now that we shall be discussing a few thermodynamic aspects before we go to discuss about this. What are those? You know that till now we have introduced about this ideal cycle, actual cycle, all those things, but it is not possible to have any cycle to be ideal cycle. So, we need to consider the actual cycle. So, which cycle should be considered to represent the processes which are there in a power plant? Rather, which cycle, I mean the processes which are there in a power plant should be, you know, mapped following a particular cycle, thermodynamic cycle. So, which cycle should be considered? So, the choice of any particular thermodynamic cycle depends on two important quantities. So, choice of a particular thermodynamic cycle it depends on two quantities. One is the operating or the running cost of the cycle or plant, and number two is the capital cost, or sometimes it is known as initial cost. So, whether any particular cycle should be considered or selected, that largely based on the consideration of the operating or running cost and the capital cost. Operating and running cost depends on the thermal efficiency of the plant, while the capital cost or initial cost depends on the size as well as complexity of the plant. So, I am going to discuss this. So, this particular aspect which depends on the thermal efficiency of the plant, while this particular aspect depends on the size and complexity of the plant. Okay. So, I am discussing because this is again the name of the course is Thermal Engineering Basic and Applied. So, these points you should know. So, any particular thermodynamic cycle that should be considered to compare the processes of a real power plant will be selected based on these two important points. One is operating and running cost, other is capital cost, and again I have mentioned these two. So, you know that. So, next I am coming to discuss about one important rather two important performance measuring parameters, thermodynamic aspects. So, fine, we have, if we can represent all the processes in the thermodynamic planes or ordinate diagram, and then also we can compare them with any thermodynamic cycle, but eventually what we need to do, what next? Basically we need to measure the performance. So, when we are trying to measure the performance, which particular index will be used to compare that? Let me repeat it. So, you know that we know that efficiency ratio or the whatever I have written here, that efficiency ratio or relative efficiency, one is the very good for the maximum work output, maximum performance of the best performance of the plant, but it is very much unlikely that the efficiency ratio will be 1, but our target should be to get closer to 1. Now, when we come to know that the performance of this particular cycle, because the cycle should be the actual cycle. So, when we are trying to compare different actual cycles, we need to define the performance measuring parameter which should be used to compare the performance of different actual cycles. So, accordingly here we can write the performance measuring parameter or index. One is known as steam rate or specific steam consumption. That is SSC, specific steam consumption. What is that? So, steam rate or specific steam consumption is one of the one important index, right, which is used for the comparison of the performance of the steam power plant. So, this is important index which is used for the comparison of the steam power plant. What is that? So, you know that it is mass flow rate of steam per unit kilowatt power developed. So, basically steam rate or specific steam consumption is defined as the mass flow rate of steam required for per unit kilowatt power to be developed. So, let me write here. So, this is nothing but the mass flow rate of steam for unit kilowatt hour power to be developed. Okay. So, this is unit power of power developed. So, basically this SSC equal to 1 by W net. So, net. So, that is very important. So, this is kg by kilojoule, right. So, what is kilojoule? So, that is 1 by W net, this is kilowatt second, right. So, that is kilowatt second, but according to the definition we need to know kilowatt hour. So, we can write it, that is 3600 divided by W net kg kilowatt hour. Okay. So, I will be writing over here like this. Okay. So, now I have introduced again one another term, that is W net. What is W net? So, W net is the net work we are getting from the power plant. So, now you know that the specific steam consumption is nothing but the mass flow rate of steam, that is per kg for unit power to be developed. So, if you would like to develop 1 kilowatt hour power, what would be the requirement of the mass flow rate of steam? So, that is the specific steam consumption rate. I will come to this particular point again, but before that, since we can see that this SSC is related with this W net, what do we mean by W net? So, for that let me define a few things, that is positive work, that is W positive, and negative work, that is W negative. So, net work W net equal to W positive minus W negative. So, what is W negative? If we go to the first slide, wherein we have drawn the schematic depiction of the plant, you know that we are getting this amount of work from this plant, but a small, or I do not know, a certain fraction of this work should be supplied to pump for its operation, right. So, we are supplying heat at the cost of this input energy, we are getting some amount of energy in the form of work, but a certain fraction of this output work or output energy must be supplied in the form of work to the pump for its operation. So, this W net, if you try to look at, as if this W into the pump appears to be the negative work, while the W out, which the work which is coming out from the turbine, that is the positive work. So, basically this is the positive work that we are getting out from the system, while this is the negative work that we are supplying to the system. So, eventually the net work should be W out minus W in, that is what we are getting, right, because certain fraction of this work should be supplied here. Okay. So, that is why this W positive and W negative is these two positive and negative work is coming. Now, so this the ratio of this net work to positive work is known as work ratio. So, here work ratio, you have understood that what is W net. So, W net is W positive minus W negative, that is W turbine minus W pump for this particular case. Now, this is W net by W positive, the work ratio. So, positive work, net work to the positive work is known as work ratio RW. So, this is RW. So, you can say that this is W positive minus W negative by W negative. So, we can write that RW equal to 1 minus, so this is W positive, sorry. So, this is W positive so this is W negative divided by W positive. What we can see, that means our objective should be to have net work, high net work. So, our objective should be the work ratio should be high, right, because we are getting positive work from the turbine, but this is not the work net work we are getting. So, net work we are getting is the W net, So, our objective should be to increase W net. So, work ratio should be high. What we can see from this mathematical expression is that if you would like to get higher RW, then the negative work should be less, right. So, the negative work, that is the work supplied to the pump, should be less. If negative work is high, then RW will be less and efficiency of the plant will be less. So, this is very important, that if negative work, that means the work required to be supplied for the operation of the pump is a significant fraction of the positive work, then RW will be less and thermal efficiency of the plant will be less. Okay. And for here, you know that negative work, which is also referred to back work, and this back work ratio RBW is W negative by W positive. So, this is called back work ratio. So, this negative work is also known as back work. So, this W negative also known as back work. So, the ratio of W negative by W positive is known as back work ratio. So, you know that I will be discussing again another important critical point from this particular definition, but if you would like to discuss that we need low back work ratio, high work ratio. So, low back work ratio means W negative should not be very high. If W negative is not very high, back work ratio will be less, while if W negative is less, then RW, that is work ratio, will be high. So, that is the proper combination for the higher thermal efficiency or performance of the power plant. So, if you like to summarize today's discussion, starting from the block diagram of the power plant, we have discussed about several thermodynamical issues. Then we have discussed about the need of studying ideal power cycle, and then we have seen that we have discussed that the Carnot cycle is the among the ideal cycle, the Carnot cycle is the first one. So, the ideal vapor cycle should be the Carnot vapor cycle. We have discussed that the Carnot cycle comprised of two reversible isothermal and reversible adiabatic processes. We shall be discussing the analysis of this Carnot cycle in the next class, but before that we have discussed about a few issues related to the performance of the power plant. When we are trying to compare the performance of different actual cycle, what should be the basis of the comparison, rather what would be the performance measuring parameters. To this end, we have discussed about one important index, that is specific steam consumption, and then specific steam consumption also related to the W net, that is the network. Also we have discussed about the what do we mean by network. From there we have defined the work ratio and back work ratio. With this I stop here today, and in the next class we shall discuss about the analysis of the ideal power cycle. Thank you.